So I'm going to be talking about something that's been referred to a little bit, excess low frequency flux noise, and the extended title is the history. That's what Efron asked me to talk about. So it's the historical flux noise and unusual behavior of low frequency flux noise at temperatures below 1 Kelvin. And this was done obviously by myself, Christian Urbina, who just spoke, and of course John. And I want to say thank you, John. I don't have a thank you slide in here, but thank you. And you know, it was not an easy road, but nonetheless, I think we learned some things. We'll see. All right, so here's a quick outline. First, a list of things that John suggested might be good projects to work on about 35 years ago. And then I'll talk about why we thought we could build a quantum limited SQUID. And I'll say a little bit about 1/f noise. And then show you what things looked like those many years ago, and then some of the puzzling behavior and a few conclusions. I'll try not to speak too fast. So at some point I was looking for an advisor. That was a few years ago. And I still remember going up 3rd floor Burge, knocking on the door, and someone opened it up, and we had a discussion. And you know, it was a while. I had to come back, and we had to do some reading and stuff. But John gave a list of some things that maybe were good projects to work on. And I don't have that piece of paper. I'm a hoarder by nature, but I've looked for this. But his list was, first one was, okay, well, maybe we could work on a project to use SQUIDs for biomagnetic measurements. 1/f noise, there was probably a whole bunch of other things about 1/f noise after that word, but that was one of the possible projects. Another one was the hot electron effect in metals. And the last one was quantum limited SQUIDs for gravity wave detectors. I'm pretty sure there was only 4. I mean, if I've forgotten one, sorry. And you know, one thing, if you're a graduate student looking at this is, well, which one would you choose 35 years ago, knowing what you now know? So actually, this was John's choice. I have to say, I would have been happy with any of them. And you know, they're interesting, and I'm not sure exactly why he chose this one, other than it was really interesting and hard. And he was also working on this project on MQT and other things. I should say there was another party here that got a vote, though. Nature also was present. And Nature actually chose these two. It didn't tell us for a while, but it came back and had a vote. So the basic idea of trying to use SQUIDs for gravity wave detector, or gravity detection, was based on an idea that Joe Weber had, and it was in the 50s or 60s, where you took a large piece of aluminum, several tons, and you outfitted it with precision transducers. Here's actually piezoelectric transducers. So the idea then is somewhere in the galaxy, a supernova would explode. They would emit a gravity wave if things were asymmetrical. And then you had to wait 50,000 years. Oh, you know, you don't want it to explode right next to you, so you know, somewhere hopefully far away. And then you had to give you plenty of time to build a quantum limited SQUID-based position transducer. You would attach it to your high-Q Weber bar, cool it down to 20 millikelvin, which hadn't really been done yet, but okay, that's fine. You know, it's research. And then eventually that wave arrives at the detector. It basically acts like a hammer below, a very, very tiny hammer below. It sets this bar ringing, and your position transducer, which is capable of seeing the smallest things it can see, would detect this motion or this sudden onset of ringing at 1 kilohertz, and you'd read out the waveform. Of course, this has been in the news over the last year, not this technique, or a successor to this. And this was a bold and very difficult project. So the SQUIDs that we were building at that time, this is an example of one of them. This is really a test device. It's not a working device. But it's about 1 millimeter in size, much larger than current day SQUIDs. And we were using niobium and lead indium, and the junctions were tiny by our scheme at those times, 2 micron by 2 micron on the side, niobium oxide, lead indium. And this is just one of several SQUIDs. This is what I call the type D. You can kind of see here the procedure, that I went through. And we were driving up Hearst Avenue, and Christian asked me, how much time had you spent in the clean room making these devices? I don't know. It was a good number. It took about 4 or 5 days of, we'll say, steady work to get a wafer of these SQUIDs. And there's a lot of steps in here, and that meant there's also a lot of materials and a lot of processing that went into it, and that, of course, came back in a way that would hurt us. All right, so why did I'll say John, or why did we think that we could build a quantum limited SQUID detector? And I won't really explain anything about SQUIDs. If you're part of John's group, you already know everything you need to know. So here's a look at the flux noise power spectrum as a function of frequency in a SQUID that looked just like this. And here's at 4 Kelvin. And these devices have been measured by John and others in his group for many years. And what you see is there's 2 parts. I can start using this. There's a flat part at high frequencies, we call it white noise, and then at low frequencies there's a part that increases as you decrease in frequency. And here, this I've drawn with a slope of 1 over f, and it looks really, really good like that. And we knew that, or it was known, that if you take that device, and here's the data for this one, and you cool it down, say, to 2 Kelvin, which you could do by pumping on helium, that things got better. So on this end, the white noise went down, and that's a theory that John and his students had worked through. Claudia Tesha, I remember, I still have her copy of her thesis, where he went through numerical calculations, showed that the flux noise power spectrum should scale with the temperature of your SQUID. And then there's a resistor. I should say that unlike qubits, there's actual resistors connected across these junctions, and they're at some temperature. They generate Nyquist noise. And while the SQUID's nonlinear, there's some complications, but you get a flux noise that should scale with that temperature, and indeed the white noise goes down. Now, even better, or also interesting, over on that side, there's 1 over f noise there, and that also goes down. And that's quite nice. And there was a theory for that too. This is a picture of a Dutta and Horn, which has again been applied, if you know anything about dielectric loss in qubits. This has been applied extensively over the last 10 years. And so here I've drawn not a great picture, but there's again 2 wells, and we'll think of this is either a vortex moving around, or here I've got it thinking as a magnetic moment. If it's on the left, it's down. On the right, it's up. It doesn't have to be physical space, but it can move around. In between these 2 left and right wells, there's some kind of barrier. And the idea is that if you're at some temperature, you can hop over from the left to the right or vice versa. And the larger the temperature is, the faster this goes, and there's some exponential activation. And if you were to look at the magnetization or the orientation of this spin as a function of time, it would be going up and down between 2 states. This is random telegraph noise. It was known since the 50s that this generates a Lorentzian spectrum. So that's not 1 over f noise, but it was also known that you might have more than one of those, in fact, many of them. And if you had a distribution of energies which was uniform, equally high barriers at all energies, then that gave you a distribution of the attempt times, which went like 1 over time. And you can show with a simple integration, here's the Lorentzians for one particular barrier height, and there's your density. You can integrate it out. And you just show that, that gives you 1 over f noise, and it scales like temperature. Now, there were some assumptions in there. One assumption was that those left and right wells were equally deep. And you can work out what happens if they're not equally deep effects. So there's a distribution of asymmetry, if you will, as well as barrier heights, and that would just give you a t squared. So it also would go down with temperature and still 1 over f. Now, the key thing to realize about this is this is a red herring. And I didn't know what a red herring was until John said that I was using it for something, I'm sure. There's various people haven't commented on the writing process with John, but it involves actual English, and I'm a Canadian American, and I don't really speak English, but I learned to write it the hard way, which was just repeated correction, I still have files like this thick, 1 paper, corrections. But anyway, so this is a red herring, which is to say it's deliberately misleading. It may not seem like it. We certainly didn't know it was deliberately misleading at the time, but it turned out to be. So here was the idea then, at least when I started, we knew it did this, and if we could just cool this thing down to 20 milliK, we would have a large SQUID, which we could wrap a big coil around and put it into a position transducer, and it would be near the quantum limit. This particular device, here I've drawn, there's from 2.2K down to 20 milliK, there's a factor of 100. And this, again, is power spectral density versus frequency. And it would have pushed us to, in this particular case, about 2 h-bar. So that's what we expected. And over on this side here, I've got the energy sensitivity, S of phi over 2L. That's where this h-bar just came from. So this is basically flux noise divided by inductance. It's got the right units. You can check that these are actually fundamental quantities, sort of. There are limits on what this could be in principle. But if we really could do this, we'd have to go out and build another one anyway and do a little bit better, but that would get us very near the quantum limit in principle. So that was the idea. We get a good SQUID. All right, and the problem there, of course, is that noise would be really small if this really worked, and so we devised the scheme of using one SQUID to measure another SQUID. So more SQUIDs is good. So here's a SQUID that we want to measure, and we have some inductors and a network here which allows us to put current down. This is a small resistor that allows us to fix the voltage across this one. And then if the flux changes in this device, that changes the current going through the SQUID. It has a response. The current links flux in here. That produces a flux change in the second SQUID. This SQUID is part of a flux lock loop. when it sees a flux change here, that produces a voltage error signal, which gets amplified and fed back. So in the end, the output voltage is just proportional to the flux in SQUID 2, which is proportional to the flux in SQUID 1. And we can actually calibrate the whole system, or show we could calibrate everything here with a few simple experiments. Oh, here we go. And there's the implementation. This was cut out of a niobium rod with wire EDM, and you can kind of see here's actually a measured SQUID sitting on its pads. Turns out we'd be measuring a bunch of SQUIDs, so you could just pop this off, put another SQUID in there. At least in principle, that was good. This is an RF choke to prevent too much talking going between these at high frequencies. And the measuring, or sorry, the readout SQUID, if you will, or measuring SQUID is here. The rest of the circuits are back there. And this went into a cell. You can see it, that same structure here is a flange. Wires had to be carried out. Now, some complications here that don't exist in present experiments, typically. We had a niobium tube that went around this to shield it. These are SQUIDs, very sensitive, very large devices. And we also had a copper can that goes around this. You can see some residual indium here to seal this in its own, if you will, vacuum can. And you see also here's a stem. So we would fill this with liquid helium, which was a major headache because and we were worried about thermal contact on these devices. And you can see they're mounted actually on fiberglass pieces here. All right, and here's a look. Not a great photo. I had to hunt around to find pictures. It's not always easy. I guess people didn't have cell phones. I still don't have a cell phone, but anyway. Fewer pictures existed. You can kind of see the cell down here wiring in. There's a fair amount of wires here for controlling both of the SQUIDs. And the other thing is, it's interesting. I think I got the number right, but I think this was a 20 microwatt dilution refrigerator. So you can, if you're working with a refrigerator these days, this is just tiny and this very small bore. It was a major pain in the neck to get all these wires in there and get everything stuffed in it without having some thermal contact. And anyway, we'd cool a system down. Actually, well, we vacuum can, mu metal cylinders, et cetera. Cool it down, fill it with liquid helium, and we could then measure anything from about 4K to 20 milli-K. And so here's a look at the lab. I remember it fondly in those days. Again, if you're working in a qubit lab, this is like your predecessor, sort of. This is way back when. So this is roughly, I don't know, maybe 1985 or so. And I went through this. I stared at this for quite a while. Once you get this out on a modern monitor, sort of, you can kind of look at it. Started labeling everything that I could see, and things like this copper screw. Actually, you can't really see, but you might really see there's a ladder up here. The actual mixing chamber and refrigerator and all that was back here. I especially like this C-clamp here that was holding the main pumping line onto this homemade gas handling system. That was impressive. And these Wallace and Tiernan gauges, they always just gave me confidence. There was something about the ability to read pressure with those things and look at them. They were so much better than the other gauge. If you stare at this for a while, you can see there is something missing compared to a modern lab, but I'll let you figure out that was. And I don't mean the people, but all right. So first thing is, here's a look at a current voltage characteristic for a SQUID. This is a shunted SQUID, so I realize most people don't work with shunted SQUIDs anymore. But if we go down to low voltage or zero voltage, you see it's actually a little bit tilted here. That's because of the nature of the circuit. But supercurrent branch, if you have no flux in the SQUID, you get maximum current. And if you're going to half a flux quantum, you get a branch down here or less current through it. And you could vary the flux. And you could also measure, in this case, the current versus flux through the device, nice periodic. These are all measured with XY chart recorders. I still got big files of them. Okay, so here's our partial red herring, 4K, 2K. All right, so let's start cooling it down. There's 950, 750, 510, 260, 120, 50 milli-K, 22 milli-K. That was about a week or two in my life, okay? And if you didn't follow all that, that's what it looked like. Let's say where the good parts are. Well, there's a theory. That wasn't one of them. Theory said we should have been kind of down there. So first thing was, over here in the white noise part, that the white noise did decrease by about a factor of 20 from 4 Kelvin, so that left us at about 200 milli-K nominally, or what it was effectively like that. And actually, we did figure this out. This took a while, but that was one of those things on that list. We figured out was due to the hot electron effect. And if that hadn't been on the list, would have never figured it out, I'm sure. And I don't know why it was on the list. I don't know how you knew it should be on the list. I mean, it was just, one of these crazy coincidences. But anyway, effectively, we were putting power onto this device, not much. And it just was self-hitting, if you will. It was electrons actually in those shunts losing thermal contact with the phonons. That was a solvable problem. Now, over here on the other side, that 1/f noise, which looked so good from 4K to 2K, actually went back up. And the first point at 95 millik was already, sorry, 950 millik was already headed back up. And that was a major disappointment. I'm not convinced, I don't remember if I knew I was in trouble at that point, but I had some inkling of it, I'm sure. That's right. All right, so here's, if I just pick off the noise at 1 hertz, and this is now in root mean flux, power spectral density rather than the power spectral density, there's a square root in there. So these are now in microflux quantum per root hertz. Here's just at 1 hertz the magnitude of that noise. And you can kind of do this. I'm going to separate it somewhat artificially into 2 parts. There is a section, that promising part up here, which actually is, I'll call it a high temperature 1/f noise. And we actually found later that, or as we built more devices, that did depend on the material the device was made of, depending on the superconductor. It seemed to be coming out of the niobium. And it happily went away actually quite rapidly, faster than T/f, but like T²/f for the power spectrum. That was a good thing, and if that had continued, we've been in really good shape with the excess noise. On the other hand, there was something, it was very hard to know what was going on here, because that was a hard region to operate in, something that showed up and kind of took off and took over as we went on. And there is a curve on here, and it's, I guess it'd be a blue herring or something. It's got some truth in it, but it's a complete lie. So probably. So this curve actually is the reduced saturation magnetization of spin 1/2 magnetic field. You can go into Cattell, and there's a little formula there, and it just gives you something that turns on as you go down to low temperature. And you could play around with spin 1, 3/2. They all look very, very similar, so there's really nothing definitive here. All right. So the question is, okay, that was one device. Well, actually, it was many devices already at that point. But what if we build another one? This is a device which actually has these large pads on it. They're connected to the shunt. These are made of gold copper. These are cooling fins to try to cool down those electrons that were getting too hot. I mean, it was a futile wish, I'm sure. But one thought was, well, maybe if we cool the electrons down, this noise will go away. And of course, it would make the white noise better, and that would all be good. So here's what some of those devices looked like. So here I have a couple devices, D1 and D2, black and blue, without those cooling fins, and M1 and M2, which did indeed get much colder in the white noise. But you see, actually, there are some differences. There's some variation here, but they're all doing very similar things. And so that meant, A, we didn't solve the problem by getting electrons cool, and B, we actually have a reproducible phenomenon, at least that we build devices that look similar. They did similar things, if not identical. That was important because it wasn't really clear what was going on here at all. Here's an example of a different looking device. I'll show you a whole bunch of them after a while. But this one is about 10 times smaller. You can see here, this is now a 100 micron scale, and it's got just a 2 micron line width. So it would fit comfortably inside of one of those other SQUIDs, and this is just a photograph of one before it was made. You can actually see some of the junctions here. These are the shunts, et cetera. And here's the spectra of those 2 devices. So this is the flux noise spectrum of device M1, which had this large size, large shunts. And here's this device, which is a good deal smaller. And you see it also showed 1/f noise. But you can see right away that there's something odd here, which is that they have different slope. So in other words, the 1/f of this large device, it went like 1/f to the 0.92, whereas this guy with the very narrow line went like 1/f to the 0.67. And I should say, so that this something about the size or shape, symmetry, geometry of the device or the SQUID is changing the slope. And there's something very puzzling about this, because here, if I draw these 2 devices to scale, that's about how big F1 is. It's a little guy measuring presumably what's going on in some small region right around it. And if I were to imagine that there was some noise source everywhere, and I added it all up, added it up all over the area here, there's no way I could get, by adding up a whole bunch of 1/f to the 2/3 noise, there's no way I can get 1/f, at least if the noise is correlated. I would just get more 1/f to the 2/3. So this was very strange, but it suggests there's something funny going on. There's some spatial correlation or something. I can't just sum up the noise over the area. Okay. All right, so what do? You build more SQUIDs. You build more SQUIDs. You hunt. Those are big ones and small ones. You measure them, and they all have 1 over F noise. This is called desperation. You're just trying to make it go away. Okay, let's make some small ones. Let's make some big ones. Let's put more lead, less lead. Let's change the substrates. Smaller ones did have somewhat smaller noise, but there's only a factor of 2 here, despite a factor of 100 difference in the area between the SQUIDs. Didn't seem to come from the superconductor. We tried different things, different portions of material. We tried a few substrates. That didn't matter. Anything else we tested, none of that mattered. Here's a look at the slopes of the different noise for the largest devices. Here's a few. Here's some, if you will, medium-sized devices. Here's some smaller ones. So the alphas, the slopes were getting smaller. And there's actually more devices just as a subset. But it was only the biggest devices that had things near unity. All right, so I want to get to the 8 mysteries or miseries. This caused uncounted nights of lost sleep, including last night. Still, anyway. So what is the physical source of the noise? Okay, so Christian actually had, by far, I think the best guess, paramagnetic impurities. This was, this is what I remember. He said that was the go-to thing if you had trouble in NMR. And that was, I think, a really good guess. Why does the noise increase below 1K? Something bad happens. We didn't know what it was. Is the noise in thermal equilibrium? Is it being driven by the SQUID or by some external source? Yes, I think that pretty much limited the options. Or hopefully there's nothing else there. And why does the noise only depend weakly on SQUID size? This we actually understood at some level. If you have a local noise source covering the SQUID in 2D, it turns out it would still depend on the aspect ratio, but not the overall scale factor. How can the slope depend on the size or shape? It has to be spatially correlated, I think, although maybe there's something else bizarre going on. And what leads to alpha of 2/3? I'll say physics. I don't know what physics, but must be some physics there. And how do you get rid of the noise? Hire Rob McDermott. You'll see him next talk. And the one that was most troubling, I think, certainly personally, psychologically, was, did anyone else see this noise? So there's trouble with going down, at low temperatures and looking for something for the first time, or finding something that you weren't looking for. And actually, Michelle was commenting, and that's why I kind of asked, did you really want to see a violation of quantum mechanics? And the correct answer is no, you really don't want to, because if you see a violation of quantum mechanics, you're just going to be tortured, whether or not you made a mistake, whether that's right, did anybody else see a violation? It's hard, it's very hard. And for me, what was really hard was knowing whether I had messed up, and that's why many SQUIDs were required, and looking at things in many different ways. It was very difficult. So in '87, we put out a paper. That's about 30 years ago now, and it showed. I think Christian showed an example of this. Showed a bunch of SQUIDs, not all of them. We went on to measure a few after this, but they showed this increase in noise at low temperature. And also you can see this wide variation in some of the high temperature stuff. This was, again, due to the amount of lead in the device. Okay, so it took a while, but one reason why we're here today, congratulations Irfan on center. Congratulations John on the center. Was because this actually had some importance. Here's a slide actually from the Decoherence and Superconducting Qubit conference that was held about 9 years ago at Berkeley down the Marina. And Nakamura showed a slide where they measured dephasing in their flux qubit and inferred a noise of about 2.3 microflux quantum per root hertz at 1 hertz of 1 over F noise. There were some assumptions behind that, but he had some very nice data. And this, I don't know if this was the first, but it was the one that someone wrapped a number on there with 2 digits, and I definitely noticed that. And this is suddenly at that point, or a little bit earlier, became important. So I have some technical conclusions, but I think that's not the important part. The important part is the lessons learned. That's right. So first of all, it's not always possible to predict the outcome of real experiments. If you have a real experiment, you don't know what's going to happen, or what impact it might have in the future, or how much in the future that future really is. Also, nature does not always cooperate by doing its part. Whether that means you're going to really get to 50 or 100 or a million qubits, that can be a tough road. You may think you understand what's going to happen, but that's a long way out there, and nature can be a snarling beast sometimes. So it is amazing how much trouble you can find yourself in when you go looking. This was 2 orders of magnitude, and things showed up that were surprising. And if in doubt, I think this certainly holds for qubits. Build more SQUIDs. It's a good idea. And I'd say the last thing is an exhausting search, which it certainly was, is not quite the same thing as an exhaustive search. When you've got no guidance, or very little guidance from theory, it's very hard to know, which door to open up and look in. But we'll see the next talk. So let me stop there again. Thank you, John.
So you mentioned that for a while no one saw the same noise.
Yeah.
Was this because no one was cooling similar devices down to below a Kelvin, or?
Yeah, I think it's mainly that. There were a few groups that did put SQUIDs on refrigerators for various reasons. I think the other thing is, well, and we've certainly faced issue is, you see something, you don't understand it. What can you say? That's right. We also saw some noise, and there were a few reports, but it's again a very difficult thing, right? You're not confirming or anything, or you see some noise. It's very hard to know what to do with that. So I think there were some measurements out there, but they didn't appear in the literature. I mean, and I think this is one of the things that's really quite remarkable about John. He could have just said, "You're out of there. You get somebody else." Here was something that was clearly crazy. It just shouldn't be like this. It should not have happened, right? And the instinct is, in those cases, say, okay, well, that didn't work. Let's move on to something else, right? But to recognize that this is interesting, and I don't know how he can look ahead, to qubits or why this road, was so appealing, right? I mean, it's noise. Noise is painful. Noise is hard to measure. But how do you recognize it? Oh, that's important. I mean, this was some serious time just to this one project. You heard many other projects in John's group, but to recognize that this has value and interest. I mean, he obviously is obsessed with noise, but to recognize that is not obvious. So I think other groups, they measure it fine. That's not what they're interested in, and they don't know what it is either. It made it hard, right, to do anything with it. And you don't have a real motivator, right? With qubits, you got a motivator. There's a reason why. Now you can go out and say, okay, we don't understand it, but it's important, right?
Let's thank Fred again.